So now we're going to talk about approaching infinity or negative infinity and what's happening with those y values. And this is really the idea behind end behavior. So we're asking, what is the end behavior for a function? And if you think back to 171, we talked about end behavior for polynomials, and we talked about end behavior for rational functions. And when we talked about rational functions, we talked about this idea of a horizontal asymptote. So let's kind of refresh that. Start with our rational functions. When we talked about rational functions, we said it really depended on the degree of the numerator and the denominator. If the degree of the numerator was equal to the degree of the denominator, then the horizontal asymptote was the line y equals, and it was the leading coefficient of the numerator divided by the leading coefficient of the denominator. So if the degree of the numerator was less than the degree of the denominator, then the horizontal asymptote was the line y equals 0. And then if the degree of the numerator was larger than the degree of the denominator, then there is no horizontal asymptote. Now, when we talked about end behavior of polynomials, we talked about the degree and the leading coefficient. So if the degree was even, or if the degree was odd, and if the leading coefficient was positive, or if the leading coefficient was negative. And we could kind of create a chart as to what's going on. So if we had an even degree with a leading coefficient that was positive, we could think about something like x squared, where both ends are going to point up. If the leading coefficient was negative, then both ends were going to point down. If the degree was odd and the leading coefficient was positive, we could think about like x cubed, where the left-hand side goes down, right-hand side goes up. And if we reflect that and look at negative x cubed, left-hand side goes up, right-hand side goes down. So everything that we talked about in 171, these two pieces can actually be derived, if you will, from calculus ideas. And that's what we're going to really talk about here. So we're really thinking about end behavior, which means what happens when x gets super big or x gets super small. And that's the idea behind taking the limit as x approaches negative infinity, because that's going to give us really small x values, or as x approaches positive infinity, which will give us really big x values. So let's look at theorem 2. Now, p is going to be a positive real number, a k is going to be any number except 0. And we're looking at a couple of examples here. These two are going to deal with rational functions, and these are going to deal with polynomial functions. So these are really iterations of your basic power functions here. If we take the limit as x approaches negative infinity of k over x to the p, then that's going to be equal to 0. That's really following the second rule down here for rational functions. Notice this is a rational function. This is just some number, and this is x to some power. Notice the degree of the bottom is larger than the degree of the top. So this is heading to 0. So an example of that would be something like this, where I'm approaching maybe 3 over x to the 5th. So what's happening here is when I plug in super small values for that denominator, then that denominator is getting larger and larger and larger as I go further and further and further to the left on that number line. So if I take the number 3 and I divide by something that is super, super small, all of those numbers are getting closer and closer to 0. The same thing's true if I approach infinity. I'm going to use that same power function. So as x gets bigger and bigger, and I take that and I raise it to the 5th power, I now have 3 divided by something that's super big. And as x gets bigger and bigger, because we're going further and further out on that number line towards infinity, then that whole fraction is shrinking and it's getting smaller and smaller and smaller, which is why this rule down here, that second rule, holds true when that numerator degree is smaller than the denominator degree. The second two deal with power functions. And what's going to happen here is if I have a function, maybe this is something like 3x to the 5th. I want to know what happens when x gets really small or really large. Well, with polynomials, I'm going to either head off going to positive infinity or I'm going to end up going to negative infinity, really depending on what that leading coefficient in that degree looks like, which is where this chart from 171 came from. So then the question becomes, well, how do I know if I'm going to infinity or negative infinity without graphing it, without memorizing this chart for a polynomial? So we're going to do some fun factoring here. I'm going to scroll down so we have a place to write this. So this is matched problem 3. We're looking at the polynomial negative 4x to the 4th plus 2x cubed plus 3. We want to know the limit as x approaches infinity and as x approaches negative infinity. Now, we already know what's going to happen. We know the degree of this polynomial is 4, and we know the leading coefficient is negative. So based on that information, if we go back to our chart, we have an even degree polynomial with a negative leading coefficient, which means that we should be heading to negative infinity as x gets smaller and as x gets bigger. But let's show that algebraically. So what we're going to do, there's a couple of different ways to do this. Here's what I like to do. I'm going to factor out that x to the 4th, and I'm going to factor out the negative. So when I do that, that's going to leave me with a 4. That's going to leave me from that first term. So multiplying back through would give me that negative 4x to the 4th. And if I factor out that negative x to the 4th from that second term, we're going to have a negative 2, but it's going to be a negative 2 divided by x. Okay, think about redistributing. If we were to redistribute that, then that would give us a positive 2x to the 3rd. So that factoring is correct. And then same thing with that last term. I'm going to factor out a negative. That's going to leave us with a minus 3 here over x to the 4th, because if we were to redistribute, we would have a positive 3 x to the 4th over x to the 4th, which gives us that positive 3. Now, the reason I would want to factor that way is because I want to think about taking the limit as x approaches infinity. So let's look at this. We know the limit of the product is the product of the limits. So I could use that property from that last section and think about it this way. And that's going to be times the limit as x approaches infinity of 4 minus 2 over x minus 3 over x to the 4th. So let's think about what's happening here. So as x gets bigger and bigger and bigger, I am going to take those big numbers and raise it to the 4th power, and I'm going to multiply it by a negative 1. So this limit is actually heading towards negative infinity. Now let's look at this piece. I'm multiplying negative infinity, or the idea of negative infinity times something. So if I take the limit as x approaches infinity for 4, I'm just going to get 4. Okay? But as x gets bigger and bigger, then this second fraction is getting smaller and smaller, so that is heading to 0. Same thing's true with this. As x gets bigger and bigger, that's heading to 0 as well. So I've really got this idea of this negative infinity times a positive 4, which is still heading to negative infinity. So we would say that limit, that end behavior is heading to negative infinity. Now we already knew that because of this idea up here. Let's now look at what's happening as x approaches negative infinity for this function. I'm going to move this down. So same thing. I'm still going to factor it the same way. Still split it up the same way. Approaching negative infinity. So if I think about this idea of plugging in super small numbers in here, I'm still going to be heading to negative infinity for this first piece. Now the second piece, the limit as x approaches negative infinity of 4 is still going to be 4, but this is going to go to 0 and this is going to go to 0. So I'm still heading to negative infinity in that direction. So just for fun, let's graph this one. If I go to my calculator, so we already knew end behavior. So here's our graph. So as x gets smaller and smaller, you can see how those y values are heading towards a negative infinity. I'm going to go to the table just to show that. So I want x to get smaller and smaller, so like negative 10, negative 100, negative 1,000. So you can see how those numbers are getting smaller and smaller also. So likewise, if I look at the right-hand side and I get numbers that are bigger, my y values are still getting smaller and smaller, and they are still heading to negative infinity. So everything we have done matches up with that table of end behavior values that we talked about in 171. So there's the end behavior for that polynomial. So we could actually think about this in a different way. And we could look at the polynomials in terms of their leading coefficient and really that first term, that leading term, if you will. So let's look at these. Let's say we want to take the limit as x approaches infinity and as x approaches negative infinity of these functions. Well, it turns out that first term, if we were to write this in descending order, is going to outweigh everything else that happens in that polynomial. So we don't actually have to factor out that negative and that leading x to that power. We could just think about what is that leading term. So if I were to rewrite this, my polynomial function would be negative 4x to the 5th. plus 300x squared. And I got to say, this is going to outweigh everything. We could factor out that x to the fifth, and we would end up with a fractional term here that has an x in the denominator. So we could say that this is really going to mimic this, and then we could figure out what's going on with that. Well, as x gets bigger and bigger and bigger, then this is going to head to, I'm going to write it this way just so you can see what's going on. This is still going to be positive infinity, and negative times positive infinity is going to lead us down to negative infinity. So we would say the limit as x approaches infinity for this polynomial would mimic what happens as the limit approaches infinity for negative 4x to the fifth, which is going to head to negative infinity. Likewise, if we look at the limit as x approaches negative infinity for that leading term, so we would have negative 4 times super small number, which I'm going to write as negative infinity to the fifth. Well, this is still going to be a negative number, and a negative times a negative will end up giving us a positive number. So we would expect as x approaches negative infinity, these y values to get larger and larger and larger. Okay, so let's go back to that end behavior chart that we talked about. The degree here for this polynomial is 5. That leading coefficient is negative. So our end behavior chart would say that this would mimic something like a negative x cubed, which means it would look like this. And that's the same thing as what we ended up with here. As x gets smaller and smaller, those y values are getting larger and larger. And as x is getting larger and larger, those y values are getting smaller and smaller. So you're going to get the same conclusion either way. But whatever conclusion you get should always match up with that end behavior test from 171. So let's look at B. We're looking at the polynomial 300x to the 6th minus 4x to the 5th. This is already written in standard form where those degrees are descending. So we could examine the limit as x approaches infinity of that leading term, and the limit as x approaches negative infinity of that leading term. That leading term has a lot of power because of that exponent. So as x gets larger and larger and larger, these y values are going to head towards infinity. As x gets smaller and smaller and smaller, I'm also going to head to positive infinity. Now, if we were to go back and use that end behavior chart, you're going to see how this does match up. Our degree is 6, our leading coefficient is positive, so this should mimic what x squared looks like, which we would expect both sides to point up. So as x gets smaller and smaller, the y values get bigger. As x gets larger and larger, those y values also get bigger. So for me, it doesn't matter which way you go about examining this. If you want to use that end behavior chart from 171, realizing it's based on this idea of calculus, that is fine. If you want to use this leading coefficient idea that we talked about here, that is fine. And if you want to do that factoring that we talked about in the last problem to figure out that end behavior, where we factored out a negative if there was one, and then that leading term, then that is fine also. Every one of those will give you the same result. You'll get that same end behavior. So it doesn't matter which way you do it. The end goal is to figure out that end behavior.